few people who've requested a Zoom recording. Okay, wow, welcome. It's wonderful to see everyone here. We have such a diverse representation, I guess, from the universities, from industry, and so many community groups. My name is Sabin Zahirich. I'm a geologist at the University of Sydney. And we're incredibly fortunate to have so many experts here actually tonight who have flown specifically interstate for this very event. So for example, we've got Dr. Daria Guerrero, put your hand up there, who's flown in from Brisbane, and Professor Megan Miller from Canberra from the Australian National University. So thank you so much for coming all this way. And of course, I'll introduce all the speakers in a moment. Just in terms of logistics, the council have asked me to just remind everyone, the bathrooms are here on the right if you walk out. If there is a fire alarm, we need to evacuate through the front doors and a little bit further down the street. I think they said not to go through here because then we'd be trapped and we don't want that. The way tonight will run is a series of short talks. So everybody will talk about their disciplinary expertise. So we'll talk for a few minutes and then we'll have a joint panel discussion where we invite questions from the audience. But really the most important thing is that the reason why we're here and why we're so passionate to reach out into the community is that we were really shocked at the disaster that we saw unfold in February this year in Turkey and Syria. Okay, those earthquakes were devastating and they've cost somewhere around probably at least 60,000 lives. And so the reason we're gathered tonight is really to try to communicate what we know about those earthquakes, what we know about earthquake science, and how can we reduce casualties in the future, right? We don't have a way to predict earthquakes. We don't have a way to control earthquakes and prevent them. But, you know, based on the seismic hazard maps that you see in front of you, we do have an idea of where the earthquakes will be recurring and what kind of magnitude of earthquake we might expect. So we can use that in any planning decisions in terms of building communities and rebuilding communities. So I'd actually, we discussed this and I'd actually ask that we have just a moment's silence to acknowledge everyone's grief and loss over these last few months. Okay, so the reason we decided to hold this event in May was to focus first on that relief and recovery mission. People were still grieving, but hopefully tonight we can discuss ways that we can move forward and try to minimize casualties in the future, as I mentioned. So I just want to thank everybody involved in organizing, so the Geological Society of Australia for their support. We're keen to reach out to the community, to high school teachers, many of them who are here. Thank you. Thank you for all the amazing superhuman work that you all do. You're welcome to join us at our free monthly events. I want to thank the University of Sydney for their support. We've got Professor Neil Coe at the back, Dr. Anne Alkuri, and Aaron Brightwell at the back here who supported this event. And Marcus Strom, for example, from the media team who helped us as well. Cumberland Council, who have given us this beautiful venue in the community itself. So a huge thanks to them. And I mentioned also the support of the Australian National University and the University of Queensland. Thank you so much. We have Shelby Trainer here from the ABC. Thank you so much for coming and covering the event. Shelby will be available after this event to talk to anyone. If you want to have a chat with Shelby, stick around. We also have a representative from SBS Turkish. So it's great that there's some media coverage. And of course, I want to acknowledge the traditional owners of the land upon which we meet, the people of the Eora Nation. I pay my respects to their elders past, present, and emerging. So here's the team. I mean, I'm there. I'm here really running the logistics, making sure the lights are on and so on. But the superheroes behind this, we've got Professor Megan Miller from ANU, Dr. Derya Gurer, Dr. Sinan Zaiden, and Dr. Aaron Opdyke from various universities, Sydney Uni, and we've got Dr. Vasilis Chatsaris at the back here, who will all talk in order. And so I'll just open up with some general words. And given the big challenges that we face as a society, whether it's climate change, food security, energy security, I believe that earth scientists and engineers are key to, hang on, I'll just admit everyone. These experts are keys to addressing these huge challenges. So for example, ensuring that we have potable water for growing populations, that we're bringing people out of poverty through our natural resources. To deal with climate change, we need more renewable energy. And to build that renewable energy, we're going to need more resources and materials such as copper and rare earths and other critical minerals. To mitigate, observe and track disasters, we need more Earth observation, okay? Satellites, geographic information systems, and there's a lot of great work in the School of Geosciences at the University of Sydney and lots of other places around the country. And also to ensure continued economic growth and development. So hopefully that gives you an idea of some of the challenges we're trying to tackle. And since we're talking about earthquakes tonight, we need to talk about the forces and the mechanisms that cause or trigger earthquakes. And so for anyone who hasn't had to think about plate tectonics in the last few years, this is just a refresher. We have a rocky planet orbiting the sun. The core of the planet is about 6,000 degrees Celsius, okay? And the surface is about 15 degrees Celsius. So that temperature difference drives a process which we call convection. And Earth is really the only known planet that has this process of plate tectonics where the surface participates in that mantle convection. And so if we have a look here, we have what we call these plate boundaries, where we have volcanism, we have earthquakes and other hazards as well. And effectively, the continents are moving around as passive passengers on these conveyor belts, which are the tectonic plates themselves. And the motions we're talking about are, say, 7 centimeters per year. Australia is moving to the northeast, and that's actually fairly fast motion. So let's now talk a little bit more about Turkey and Syria specifically, and the motions that you see here are occurring over the last 200 million years. You might remember from school, this is what we call the Pangaea supercontinent, and in the last 200 million years, it breaks up, okay? And so the Turkey region here is plotted below, and you'll notice Gondwana, or this part of Pangaea, will start to rotate, and Turkey will start to collide with Eurasia here, okay? These are the continental blocks that are colliding, okay? And that gets us somewhere to the present day. So we have continued tectonic motions as a result of what's happening in the deep earth. And these stresses build up in the crust and they manifest as earthquakes, okay? When the strength of the rock is overcome by the stresses, you release that stress through earthquakes, okay? And others will talk about this in greater detail. So this is where you see the earthquakes across, across Turkey, for example. All of those red zones are where what we call active faults, okay? Seismically active regions. But you see areas that are kind of white and gray. So these are less active, less seismically active regions. So they're considered relatively safer than those red regions. So you can already see what we know from the instrumental record from mapping, where perhaps we should be avoiding rebuilding, say, huge population. So what I'll do is I'll hand over to Dr. Derya Guerrero, who is an expert on the regional geology. So thank you. Please welcome Derya.
Thank you, Sabine. And thanks for organizing this event, and to all the supporters and to all of you for being here. And Sabine said he just keeps the lights on, but actually for me personally, Sabine has been someone that has reached out right after the earthquakes as a colleague and as a friend, and has been a great resource in terms of emotional support, and has been the driving force for this event. So I would really very much like to thank Sabine and also Sabine's family for just being such good colleagues, friends. And I'm looking forward to meeting the family today, actually. So geology bringing people together in a way in a very tragic event for Turkey and Syria. And as I will show here is this region is part of a wider region, which is part of the Alpine Himalayan mountain belt, which is shown in the orange lines there on the map. And it actually spans quite close to us all the way down towards Indonesia. That's where the last bits of that mountain and seismically active region is. And the reason for this region being so geologically active, it lies actually in its geologic history. There used to be an ocean in this region that we call the Tethys Ocean. So here is a reconstruction of the Earth back to the Jurassic, so about 170 million years ago, when dinosaurs were still roaming the surface of the planet, the lithosphere, we call it amongst geologists. And what you see there is a big sea, labeled as the Tethys Sea, that separated. So through geologic time, progressively this ocean of the Tethys was lost, and it now resides actually in the Earth's interior, in the mantle. And Megan will show we can actually even image these things like with almost like medical tomography using similar methods just applied to a planetary body. So here I'm showing a tectonic map of Turkey, or geologically speaking, it's also called the Anatolian Plate. And what you see is that Turkey is extremely diverse in terms of its geology. And we have the border region with Syria down there as well. And the reason for this is that parts of Turkey and Syria have actually accreted, like with time, they became part of this mountain belt that was building during the closure of this Tethyan Sea. So what you see here is the different fragments that were once south that now are accreted to the south of this line and are a landmass. They used to be part of an ocean, now they have become part of the land through this process of plate tectonics. So we can actually go study first order plate tectonic processes, including subduction, so where an oceanic plate dives under another plate. We can study Earth's lithosphere sliding next to each other along transform boundaries. Some of us might be familiar with the San Andreas Fault in California, or closer, and here on the map is the North Anatolian Fault Zone that runs through Istanbul. Those are plate boundaries along which one plate slides next to the other. And then we can also study processes that also affect this outer shell of the planet, like mountain building and extension, like things rifting apart. So Turkey and Syria as a region are a great natural laboratory for geologists to understand these processes. And sometimes these tectonic events I study them on longer time scales, on million-year time scales, whereas really the processes can take place in seconds. So just like this recent event has lasted 80 seconds, which was for a very strong shaking event, there's processes that go for millions and millions of years, and we're getting snapshots of these processes. The geologic context for the region and why or where this earthquake occurred is actually in this triple junction between the Arabian plate, bottom right, the Turkish or Anatolian microcontinent, and then we have the Eurasian plate in the north. And now Arabia is pushing from down south towards Eurasia, and there's this Anatolian microplate in between. And as a result of this motion of Arabia pushing in, indenting, we have the Anatolian or Turkish microplate moving to the side. And in fact, it's interacting with the Hellenic subduction zone, another plate boundary down in Greece towards the west there. So this kind of deformation of the continental lithosphere can then often lead to earthquakes. It also happens in the oceans, but of course, because we are land animals, we are much more affected also by the earthquakes that occur on land, mostly except for when they're coinciding with tsunamis, for example. So over geologic time, Turkey is being extruded westwards due to this Arabian plate moving inwards, because we're going to move things out of the way to preserve kind of the distribution of those land masses. And we can actually measure that in real time, not just through earthquakes, but also through GPS. And what you see here is the GPS motion of the Anatolian microplate in the bottom right there, relative to a stable Eurasia. So if we were holding a pin on the Eurasian plate, Anatolia would be moving towards the west along that green line, which is the North Anatolian fault. But also the East Anatolian fault, which is down here, contributes to that motion as well. So it's quite complex, as you will see, and that's just a larger picture. And now more into the details of actually the fault systems. That's something Megan will talk about.
So Terry and Sabine gave a very nice introduction to why we have the large-scale processes that actually result in earthquakes. And so thought I'd start with a couple of definitions. So what is an earthquake? An earthquake is a sudden fault. So we briefly talked North Anatolian fault and the East Anatolian fault. An earthquake occurs when that fault slips. And then when an earthquake happens, it produces elastic waves. And these are what we call seismic waves. And when that fault slips, the energy is then radiated away from where the earthquake occurs and is radiated from where the hypocenter. And so the hypocenter is the epicenter. So you probably hear that in the media a lot. The epicenter is a location on the Earth's surface of where it occurs, but the earthquakes most of the time actually occur at depth. So the hypocenter has that depth information. That's very important because of the amount of shaking it occurs. The closer it is to the surface, the greater amount of shaking. So we can have very deep earthquakes down to 700 kilometers depth, but we generally don't feel those because they are so far away from the surface. And so this energy, elastic energy, is transmitted as seismic waves, and we record those on instruments called seismometers. And the seismometers record the ground motion, whether it's moving up and down or to the side, north, south, east, west, or vertically up and down. And this data is generally recorded either as an acceleration or as velocity. And so you'll see many maps talk about the acceleration of the ground. And that's why I wanted to point out that data that we're recording on seismograms are either acceleration or velocity of the Earth's surface. And so the faults that we are talking about, there's three general classes of faults. There's one that are where we have normal faults where things are pulling apart. So two blocks are moving apart. Some are reverse faults, and that's where things are coming together, like at subduction zones. But in Turkey and Syria, we mostly have strike slip faults, and that's what happened in February, and that's what has happened in the past. And so I have a little animation, hopefully this will work, showing you how a strike slip earthquake works. And so this is a near vertical fracture in the earth where the ground moves horizontally. So one plate moves past another. So the Eurasia plate and the Anatolian plate in north for the North Anatolian plate, and then farther to the south, the East Anatolian plate is an Arabian plate and the Anatolian plate moving past one another. And so when those two blocks of rocks move past one another, there's a sudden slip on them, you generate an earthquake, which then generates these seismic waves. Okay, and how this happened, there's a theory called elastic rebound theory, which provides a very basic explanation for why earthquakes continue to occur. And so the far field plate motions have been introduced due to the plate tectonics and the lithospheric plates moving on the surface of the earth. As they move, if the fault is locked or they haven't had an earthquake, the deformation or strain of the rocks, that energy of that far field push on the tectonics plates is actually stored within the rocks themselves. And eventually it gets to a critical amount, and all of that elastic strain energy is then released in an earthquake as these seismic waves, these elastic waves. And this process continues to repeat itself in these events, which we call stick slip events. And they continue to happen on a semi-regular cycle, but they're unpredictable. And it's the very key point that they are unpredictable, particularly on a human time scale. And so here is a map of the surface ruptures of the recent earthquakes, magnitude 7.8 that occurred first, and then the second one, which is the magnitude 7.6. So the 7.8 occurred in this location here, and you see that the displacement or the amount of movement on the Earth's surface was more than 5 meters. So a huge amount of motion along that East Anatolian fault. And then just 9 hours later, another magnitude 7.6, and that occurred to the north on a separate fault. So these two earthquakes are distinct. The one that occurred later is not an aftershock, but actually another main shock. And that happens when that stress continues to push on the rocks. You get this deformation, and the first earthquake changed the amount of stress in the rocks itself, and then the second one occurred. And so you can also see on this map that there are these rectangles which show other large events that have happened in the past. And so the most recent large event on the that happened prior to the February 6th one was about 500 years ago. And so there's been 500 years of stress or motion and then deformation of the rocks stored in the rocks and then released. And that's why we had these events. And so this is kind of a zoomed in version to the plot or the map that you have in front of you for the that was developed in 2018 by the Turkish Disaster and Emergency Management Authority. And so the two earthquakes that occurred in February were this one, which was on the East Anatolian Fault, and then the one separate one to the north just 9 hours later. And you'll notice that they are positioned in areas where there's lots of red. Okay, and so the red means that's where there's a lot of seismic hazard. And in this case, it's plotted in terms of the amount of ground acceleration. So how much movement, how much displacement you would get from one single earthquake. And so the redder it is, the more acceleration there is, and the more ground shaking there is, and the more devastation and hazards that can occur. Okay, and so from earthquake data, we can do seismic imaging, and this is where Sabine will come in.
Thank you for coming here, and thanks Sabine for giving the general plate tectonic context, and Daria and Megan to give the local tectonic context before. And today I'm going to briefly talk about the geophysical imaging techniques and how can we use them to understand the Earth and what's going on beneath the surface or whatnot. But the most like basic analog is to for everyone to understand is the medical ultrasound or like MRI machines, like Daria mentioned before as well. Like geophysical imaging techniques are very similar to the geophysical techniques that instead of looking at the body, we look at the earth. In the left-hand side, we see like instead of, we just put a picture of me in Greenland, and then is a Southern African model of like the different blocks of, and this is how the mantle looks there, for instance. Well, how they work? Basically, we have 4 steps in the workflow, basically. We first have a source signal of some kind. We have a physical body we want to investigate. And interactions between those things creates a response. And then using the theory, we have the model of a physical body. Another analog could be, for instance, someone trying to understand, learn how to play darbuka, dumbek, the Middle Eastern kind of rhythmic instrument. And you can think about this, the source signal of the musician here is like hand movements of the musician. And then the physical body they want to learn more about is the body of the darbuka. And then the response will be the musical sound and rhythm. And then if you do this more and more, you have a better mental model in your head to be like the, so you have the better understanding of the behavior of the instrument. And if you look at the seismic tomography, for instance, one of the most used, you can image the earth. It's like very depths, like basically, like hundreds of kilometers of length. Is the source signal in this case is the earthquakes themselves, and then earthquakes propagate through the earth depending on the properties of the layers of the earth, like you see in that image. And then we have response in different parts of the world in recorded in seismometers. And sometimes we can design them in certain ways. For instance, in Turkey, we do this a lot because it's like everyone's so interested in the extrusion tectonics and everything. And at the end, we have that type of image. For instance, a 365-kilometer depth with red and blue blobs indicating different velocity, which means like different density and other physical properties. It's a bit tricky there, but like, yeah. Well, how can they be, for instance, obviously related to like our ways of understanding the world? We briefly mentioned the subducting diving plates. For instance, have the conceptual model of the subducting plate. We hear one plate dives into another one, which creates the earthquakes. This is a similar process we see in Japan and in Turkey as well. And but not actively, but we see the real image of one of the examples, for instance, and we see earthquake hypocenters lined up quite well with this image, which is what we want to see really, and it's very assuring that the physical world actually makes sense. Another example would be my specific area, magnetotellurics. Is where you see the electrical conductivity variations of the Earth. We collect different data, but then you end up with like, again, with the red, blue blobs. And if you look at these images, they are both from Turkey. The left one is from the Eastern Anatolian Fault, where the earthquake happened, recent earthquakes. And the right one is from the Marmara Sea and the region. And if you look at the earthquake hypocenters, for instance, on the Eastern Anatolian Fault, we see lining up with the conductors. But on the other hand, in the Marmara region, we see a different comparison with the hypocenters behaving differently. So, and in general, it's a very complex image. And wherever you go, it's always the same. And it just shows like we have to study more and more and make more images like that to understand the complexities beneath the earth, to understand the earthquake generation happens. we can use these images also for very shallow engineering techniques. Like, for instance, they are more like less hard to understand and more straightforward because we deal with like places where we can reach. And in this instance, we can use them to understand the ground motions and the shakings, how much we can, the shear strength required for the grounds, for instance. And for following Vasilis, and we'll talk about more about those kind of engineering stuff. And yeah.
So where I want to focus now is what is the role of local geology. So what's happening in the local scale. And I will use the example of Marash, which is one of the cities that was impacted significantly by the earthquake. On the map here, on the right, you see the distribution of the earthquake locations shown with the large earthquake shown with the stars, and the smaller earthquake shown with the circles. And you will see that Marash, which is located in this box here, is slightly off from the main zone where the earthquakes took place. On the background here, you also see some colors, and these colors describe the change in stress or the force that is applied on the rocks. So the things that Megan talked earlier during these earthquake events. And the higher, so from green to yellow to red, there is higher change in stress, so higher force. And we see that Marash is off the red zone. Yet, 15 to 20% of the buildings in Marash city were destroyed. And there is no obvious reason why, because it's located slightly off the main shocks. Yeah. So here is a photo, an image of the Marash city. And here at the back, you can see some mountains. And these mountains consist of hard rocks. But the main part of the city is built on this plain, which consists of recent and loose rocks, unconsolidated rocks. And if you see where in this, so this satellite image here shows the distribution of the damage in Marash city. And you see that most of the damage shown with the red zones here occurred in this lower part of the city, yeah, on the plain, which is built on the plain. Now, why? So in this schematic figure here, imagine that the part of the city which was back at the mountains is here in location 3 and consists of the hard rocks. And then the main part of the city is located here in areas 1 and 2, which consists of from loose rocks, and these are underlined by hard rocks. These curly red lines correspond to seismic waves. And you see that when the seismic waves travel through hard rocks, their wavelength is quite small, but when they move from hard rocks to loose rocks, there is amplification in the wavelength. Yeah, and when they reach the Earth's surface, this causes amplification in the ground motion that we feel, and of course in the movement of buildings, and this can lead to destroying the buildings. So this is potentially something that has happened or could have happened in Marash or in other areas where there was significant damage, but there was slightly off the main earthquake locations. And someone might ask, okay, how important this could be for other areas which are quite stable, like Australia. Here what we see is a map with a distribution of earthquakes with magnitude higher than 3 in Australia. This map is from GSA Australia. And there are two main messages that we can get out of this map. The first is that earthquakes do occur in Australia. And the second is that if you see where the big cities in Australia are located, Sydney, Canberra, Melbourne, Adelaide, even Perth, they are located near seismically active areas. Yeah. So although earthquakes are not frequent in Australia, we still need to consider seismic hazard and seismic risk. And let's focus in Sydney area now. And the results that I'm showing here are from Eric Wong, who is currently a PhD student at the University of Sydney. Eric is here in the audience. Thank you, Eric, for allowing me to use your work, show your work. On the left, there is a geological map of Sydney area with the distribution of the different rock types. From light color to dark color, we go from younger to older rocks. And these light color areas correspond again to young, loose rocks. And the black lines that you see here correspond to fault zones that are known or are inferred fault zones, because we don't know exactly if they're there, but there are indications that they might be there. On the right part, we see a preliminary seismic hazard model. So the expected ground motion after a potential earthquake in Sydney area. The reason that I'm saying that is there is, and that's again, it's a preliminary model that we see. So higher ground motion corresponds to yellow and red, orange and red in this area here and this area here. And there is quite good correlation between the higher ground motion that we expect and the distribution of the loose sediments in Sydney area. By constructing maps like this one, of course, we can inform and update building codes. And with that, I will pass to Aaron, who is an engineer, and who can talk more about engineering aspects of Sydney and constructions. Thank you.
All right, so I'm going to tie it back together and talk a little bit about, and excuse my voice today, I'm just getting over a cold. So specifically, I'm going to be talking about what do we do with this information? So we can understand, how fast the ground's going to shake, how that's going to move, but how do we design our cities? How do we design our infrastructure to withstand these types of earthquakes? So just and kind of take, these. Obviously, everyone's seen these on the news in the aftermath. So just completely, all of these buildings just over. The question often becomes, why did this? So why collapse in this particular case? So one answer, which I think my colleagues have wonderfully presented, is looking at the science behind the earthquake itself. So what was so unique or strong about this particular instance? There's also decisions that we have made about how we build our infrastructure that's made it more or less vulnerable to these types of impacts. So just to put that in picture, that's an astounding number of buildings. So just imagine that. So 850,000 buildings were damaged in this series of events. Designed for these. On the one side, I'll talk a little further oceans, and we use those to design our structures. And so one way that we can look at our buildings is we can strengthen them. And so again, this is just kind of a high level snapshot of this. So, we can put some bracing in, we can put walls up. So that's one way that we've really seen as a deficit of a lot of the construction in this particular disaster. And then the second one that's coming out of this is actually liquefaction. So the soil has literally turned into water around buildings. So we can see this, if you've seen the images of buildings literally fully intact falling over, that's kind of a secondary failure mode that we're seeing that was quite common in this particular disaster. So some key challenges kind of moving forward. So a lot of my work looks at how do we help communities recover from these types of events. And so there's two big ones and key messages and takeaways. So one, which we haven't talked a lot about today, but so Turkey was certainly affected, but Syria also was heavily impacted by this disaster. So the World Bank, for example, they had estimated that more of a third of the buildings in Syria, they were already damaged from almost 10 years of civil war and conflict. So if you can imagine the earthquake affecting those buildings on top of that, they face a lot of immense challenges in that recovery process. And just getting into those areas is very political and it's difficult for organizations. So that's one of the major challenges that we see is just organizations getting resources into these areas to assist with that recovery process. But the second one for communities is how do we, and this is a broader one even for us here in Sydney, how do we weigh up long-term challenges? So if we want to invest in building safer buildings, how do we balance that versus more immediate needs that we have? And so those are really kind of a snapshot just of the big ones and maybe more of a conversation starter. So I'll conclude with that.
Good evening. I'm Tara Curlewis. I am a qualified geologist, but I also now work mainly in the area of pastoral care. Tonight, I just want to say a few things about how to respond to family and friends who have experienced a natural disaster. Just 3 points. Firstly, acknowledging the loss people have experienced is significant. People have experienced the loss of friends or family, the loss of home and belongings, the loss of that sense of security. And so to respond to this sense of loss, listening is the key. Be in touch and listen to their experiences. Do not diminish what they say, but acknowledge that what they are feeling and what they have experienced is real. Secondly, it's really important to stay connected. In the early days after the quake, there were many emergency services. Lots have left. There was wider support and from programs, international groups and local groups. And there comes a time when that wider support program will withdraw. This will leave people feeling that they are left alone and isolated. To help overcome some of that sense of isolation and aloneness, remember to call and have regular contact with your family and friends, either through the phone or emails or social media or however it is you stay in touch. And the third thing I want to say is that post-traumatic stress is real. It leaves people feeling uncertain about the future. Post-traumatic stress not only affects those who were in the earthquake and have survived the earthquake, but it may affect relatives who support family members or friends who weren't anywhere near the earthquake. So some people here tonight might be experiencing some of the signs of post-traumatic stress. If you are feeling stressed or your family members are experiencing stress from the earthquake, traumatic stress from the earthquake, then it's really important to encourage them to get some professional support, professional counselling, and to be able to talk through what they are feeling. It's important to acknowledge that the feelings are real and there is no easy way out of this experience. It's a long road, it's a slow road, but by acknowledging that what people experience is real and getting some professional help will definitely make the journey a lot easier. So thank you for coming tonight. Thank you for being interested in earth science and what makes earthquakes happen. And definitely thank you for the support you provide to family and friends who have been affected by this earthquake. Good night.